Welcome to our lecture on linear dependence and independence. Imagine you are navigating a city and someone gives you directions that just take you in circles. In linear algebra, we want to avoid that kind of redundancy. Today, we are going to learn how to identify when a set of mathematical directions gives us truly new paths to explore, and when they are just repeating what we already know. This is a core idea that will power everything else you do in this course. Let us start with a simple real-world analogy. Imagine you are giving a friend driving directions. You tell them to drive 1 mile north and then 1 mile east. These two directions are completely unique. You absolutely cannot move east by driving north. We call these independent. Now, imagine you add a third instruction. Drive 1 mile northeast. This third instruction is actually just a combination of moving north and moving east at the same time. Because this new direction does not give your friend any new ability to reach places they could not already reach, it is completely redundant. In algebra, when a mathematical direction is just a redundant combination of other directions, we call the whole group linearly dependent. Now that we understand the intuition of redundant directions, let us translate this into formal algebra. A vector is simply a mathematical object that has both a size and a direction, often written as a list of numbers. When we multiply these vectors by ordinary numbers, which we call scalars, and add them together, we are creating what is known as a linear combination. The formal definition of linear dependence asks a very simple question. Can we combine these vectors to get back to our exact starting point, the zero vector, without just multiplying everything by zero? If we can, it means at least one vector is secretly just a mix of the others, making the set dependent. This brings us to the fundamental equation used to test for redundancy. Conceptually, this formula represents a journey that starts at the origin and tries to return to the origin using our given vectors. The symbols v1, v2 up to vn represent a set of vectors, which are the directions we are testing. The symbols c1, c2 up to cn represent scalar multipliers, which are just regular numbers telling us exactly how much of each vector to use. The 0 on the right side represents the zero vector, meaning we have returned exactly to our starting point in space. If we can find a set of values for the scalars where at least one of them is not 0, but the whole left side still perfectly cancels out to 0, the vectors are linearly dependent. If the only possible mathematical solution is setting all scalars to 0, they are independent. Before we calculate anything, let us look at what this actually means visually. On the screen, you are seeing two different scenarios in two-dimensional space. On the left side, we have two vectors, v1 pointing along the horizontal axis and v2 pointing along the vertical axis. They point in completely different non-overlapping directions. You cannot build v2 using v1. Therefore, they are linearly independent. Now look at the right side. We have vector u1 pointing diagonally. Vector u2 points in the exact same diagonal direction, just stretched twice as far. Because u2 lies on the exact same line as u1, it offers no new direction. It is redundant, making this set linearly dependent. Now that we have a visual understanding, let us test this algebraically with a concrete example. We are given two vectors. v1 is 1, 2 and v2 is 2, 4. We need to determine if they are linearly dependent or independent. To do this, we choose a formal definition equation. We want to see if we can find scalar numbers c1 and c2 where at least one is not 0 that make the equation true. We set up the equation and plug in our specific vectors. The top numbers represent the horizontal direction and the bottom numbers represent the vertical direction. This single vector equation actually represents two separate regular equations stacked on top of each other. Continuing with our calculation, we will extract the top row to create a simple algebraic equation. This gives us 1 times c1 plus 2 times c2 equals 0. This equation shows the relationship between our two unknown scalar multipliers. We can easily rearrange this equation using basic algebra to solve for C1 by subtracting the second term from both sides. This tells us that C1 equals negative 2 times C2. This means whatever value we pick for C2, we just multiply it by negative 2 to find the matching value for C1. To prove dependence, we just need to find any valid pair of numbers where at least 1 is not 0. Let us pick the number 1 for C2. By doing this, we easily calculate that C1 must be negative 2. Now that we have our scalar values, we must plug these specific numbers back into our original vector equation to verify that they actually work. We multiply each vector by our chosen scalars and add the results together. The math perfectly cancels out, leaving us with the 0 vector. Because we successfully found non-zero scalars that make the vectors cancel out to 0, these vectors are definitively linearly dependent. Physically, this makes perfect sense because the second vector is just the first vector stretched to be twice as long. It offers absolutely no new direction, making it entirely redundant. So, we have proven how to test two vectors using algebra. But how do we actually test this without guessing numbers all day, especially when we have many vectors? Solving algebraic equations becomes very slow. Instead, we use a matrix, which is just a rectangular grid of numbers used to organize data. We take our vectors and stand them up vertically to form the columns of a matrix. Then we find the rank of this matrix. The rank is a mathematical measure of how many truly unique, non-redundant columns exist in that grid. This method is much faster and more systematic for larger sets of vectors. This brings us to the matrix rank condition formula. Conceptually, this is just comparing the number of unique directions we actually have to the number of directions we started with. The symbol R represents the rank of the matrix, which is the count of unique columns. The symbol N represents the total number of vectors we put into the matrix. If we have n vectors and the rank R is exactly equal to n, it means every single vector is unique. Therefore, they are linearly independent. However, if the rank R is less than n, it means our grid contains fewer unique directions than the number of vectors we started with. This physically means at least one vector is a redundant combination of the others, making the entire set linearly dependent. Now let us look at a slightly more complex example using 3 dimensions. We need to determine if the vectors 1, 0, 0, 0, 1, 0 and 0, 0, 1 are linearly independent. Instead of the algebraic equation, we will use the matrix rank method because it is much faster for larger sets of vectors. We will form a matrix, which we will call A, by standing our 3 vectors up as vertical columns, side by side. Notice that this specific matrix has ones on the main diagonal, from top left to bottom right, and zeros everywhere else. In matrix algebra, this special grid is known as the identity matrix. Our next step is to determine the rank of this matrix. Continuing with our matrix, we need to find its rank. To find the rank, we look at the number of non-zero rows when the matrix is in a simplified step-like form. Because our identity matrix is already as simple as possible, we can just count the rows that have at least one non-zero number. There are exactly 3 non-zero rows, so its rank R is exactly 3. Now we must compare this rank to the number of vectors we originally started with, which is n equals 3. Because these two numbers match perfectly, it proves that none of the vectors are redundant combinations of the others. Physically, these represent the standard horizontal, vertical, and depth axes in 3-dimensional space, which are fundamentally independent directions. Before we conclude, let us understand why linear dependence is absolutely crucial in almost every field of science and engineering. In structural engineering, if the forces acting on a bridge form a linearly dependent set, it means the structure might have redundant supports, or conversely, it might be missing a crucial independent support to keep it stable. In computer science, specifically in data compression, algorithms look for linearly dependent data points. Because dependent data is redundant, the computer can delete it to save file space and just mathematically rebuild it later. In robotics, the joints of a robot arm must move in linearly independent ways so the hand can reach any point in three-dimensional space without getting stuck in a redundant loop. Without this concept, we would waste massive amounts of resources. We have covered a lot of ground today, so let us reinforce the most important ideas. First, linear independence is fundamentally all about uniqueness and efficiency. A set of vectors is linearly independent if every single vector contributes a completely new direction that cannot be faked by mixing the others. Second, if even one vector can be built by combining the rest, the entire set is linearly dependent and contains redundant information. Finally, remember our two testing tools. We test this either algebraically by trying to combine them to make zero, or by checking if the rank of their matrix equals the total number of vectors. You now have the tools to identify redundancy in any mathematical space. Great job today.